Question 4. Owen collects data about household expenditure on food. He records the weekly expenditure on food for 80 randomly selected households from across Wales. So we have the data here going from a household that's expenditure is less than 40, and then grouped intervals going up to last one, x is greater or equal to 90. Part A, explain why a normal distribution may be an appropriate model for the weekly expenditure on food for this sample. A normal distribution is a bell-shaped, symmetrical distribution with the highest probabilities near the centre and then getting less and less slightly near the extremes. So if we look at this data, 18 is the highest probability at the centre, 16 and 15 are very much the same symmetrically either side of the 18. Then we've got 11 and 9, and then we've got 5 and 6, so getting less and less. So this is a symmetrical bell-shaped distribution, so it could be an appropriate model for this table of results. Owen uses the distribution, which is normal, with the mean of 64 and a standard deviation of 15 to model expenditure on food. He wants to find the number of households in the sample that this model would predict to have weekly food expenditure in the range 60 to 70. So we want the probability that this normal model has a weekly expenditure between 60 and 70, and then from that we should be able to calculate the number of households in the sample, because our sample was a sample of size 80. So we're going to use the Classwiz Calculator. So we switch it on and then use menu 7, which is the stats menu. So we get a normal probability distribution or the normal cumulative distribution. We're going to be calculating the probabilities over an interval, so we want to use the cumulative distribution. So if we press 2, so we get this display normal CD, the lower limit, so we feed in the lower limit was 60, the upper limit is 70, the standard deviation was 15, and if you scroll down you get the mean, and you can feed in that the mean was 64. And if we press equals, this gives us the probability of 0.2606. So the probability that household expenditure is between 60 and 70 is 0.2606. But we know that there were 80 households in the survey. So we times this by 80 and we get 20.848, and then we'll round that up to 21. We have 21. Part 2, we want x being greater or equal to 90, so we want to find the probability that x is greater or equal to 90 and then use it from the fact that there is 80 households. So we go to the normal CD again. Our lower limit we can feed in is equal to 90. Now the upper limit, we've got to decide what we're going to use for the upper limit. In a normal distribution, we should find that the range of the values should lie between the mean and plus and minus 2 standard deviations. So nearly all the data should lie in that range. So this is 64 plus or minus 2 times 15, which means that we have a highest value roughly of 94, a lowest value of 34. So we could perhaps put in an upper value of 120, which is way outside this range, but we know that we will be absolutely certain that that will give us the correct probability. We will still have the mean, the standard deviation and the mean from earlier. So we will put that in and just press equals to get our result. And we get an answer of 0.0415, but there were 80 people in the sample, so we times by 80 and get 3.3214. So there are roughly 3 households, if we round down, that are greater or equal to 90. So if we look at our original table of results, we got an answer between 60 and 70 of 21 households, and we got an answer of greater or equal to 90 of 3 households. So our 21 is too large, and our 3 is too small. Part 2. Explain how R1 could improve the model by changing one of its parameters. Well, the parameters of a normal distribution are its mean and its standard deviation. So let's think about how these parameters could change the model and the results that we got. We could look at this a little bit if we use Geogebra, and here we have, if we look at the blue graph and we change the mean, as we change the mean, the curve just slides along, staying the same height, so it's just a translation of the curve. Let's see what happens if we increase the standard deviation. The curve gets flatter and more spread out. If we decrease the standard deviation, the curve gets higher and thinner. So this should help us when we go back to the question. So this is what our normal distribution curve would look like. We had 21 in this region here and 3 in this region here. So if we increase the variance, we spread out the curve, and I try to draw a green curve which has become flatter, and we've lost this red area. So there was 21. This could mean that underneath we now have 18. There was 3 here, and this would have increased, so this area could now be 6. So the idea of increasing the variance would be a way of getting better results. Part D. Owen's friend Colleen wishes to use the improved model to predict household expenditure on food in Northern Ireland. Comment on this plan. The plan could be a reasonable plan because Northern Ireland and Wales are both in the UK, so the costs should be reasonably the same. So we could argue from this point of view that the plan could be reasonable. But conversely, that Northern Ireland is distinct from Wales and may not have the same shopping habits in Northern Ireland as they do in Wales, because the data was prepared from a sample from Wales, so you could argue that it wouldn't be a reasonable model to proceed to try and predict household expenditure in Northern Ireland.
Here we have the data that Aaron collected presented as a probability histogram, and so what that means is that if we multiply the width of the bar by the probability here, that will give us the probability of a household being in this 60 to 70 region. So we can now look at the normal distribution that was used to model it, and we can see that it doesn't look great. It's not too bad, but it doesn't look great. So we'll now put a variable one on, and you can see these deltas up here. In fact, I'll put that back to 0 before I put the other one on. And so that's the original one, so no change in the standard deviation. So we've got delta sigma here, and we've got delta mu here. So we have delta sigma here, which is change in the standard deviation, and delta mu here, which is change in the mean. So, as the question suggests, we can increase the standard deviation, which spreads the distribution out. I'll just get rid of the original so we can see the new one more clearly. And of course the reason it spreads it out is that if we go from the mean, which is around the 65 mark, then if we now go 15 plus the 2.2 as the standard deviation, so if we now go 15 along and another couple, it means that this part here from the mean up to the first standard deviation will have 34% of the distribution. So as we increase this, it means that we go further along to gather the area of 34, so it must come down. So that's looking reasonably good. We may decide we would want to tinker with the mean a bit. Notice that with these bars we can see that this bit here is sort of outside, but it balances with this bit here, so we can sort of think of that as about right there. This one's about right. We've got this bit and this bit balancing this bit and this bit. For this one, we have to remember that although I've drawn the bar just going up to, I've rounded it off to 95, in fact 2 standard deviations from the mean was 94, as was pointed out in the solution, but that doesn't mean that there couldn't be 1 or 2 of the 6 in this, the 6 households represented by this bar that weren't a bit higher up. So it could be that this actually should be going more like that, which would fit the curve better, and similarly at the other end. So that's not bad. We might try playing around with moving the mean just to get a better fit. Of course, in reality, all this data would be put into a computer program, and then the program itself would be able to faff about with the data to make the normal curve fit the data as best it can. With only 80 households, that's not a great deal of data, so there are limits, but a computer program would faff about by playing with these parameters, so we're just doing it by eye here in Geogebra.